Hello, today we're going to be talking a little bit about probability theory and density estimation. A basic concept in probability theory is that of the random variable. A random variable is a variable whose outcome is determined by an experiment or observation. Here we have a coin being tossed, and the potential set of outcomes is called the sample space. For the coin, it's heads or tails, of course. Another concept is that of an event. An event is a subset of the potential outcomes to which probabilities may be assigned. Possible events in this case include heads, tails, either heads or tails, or neither. And each of these events does have a probability or a number between 0 and 1 assigned to it. This event has probability 0.5 in a fair coin, 0.5, 1, and 0. Just to be a little bit more formal, probability is the likelihood that an event A will occur, and probability can also be thought of as a function that assigns to each event or subset of the possible outcomes a real value in the range of 0 and 1 inclusive. And probabilities follow just these three axioms, and anything else you've heard about probabilities can be derived from these. The first is the measure axiom, which says that if you have the entire sample space, the probability is 1 of the entire sample space. Non-negativity, that any event A has to have probability greater than or equal to 0. And additivity, if two events are disjoint, meaning they don't have any of the same outcomes in common, or they're not overlapping in any outcomes, then you can just add up their probabilities. A probability mass function is another useful concept. It's a function that assigns probabilities to every outcome. So suppose we had a random variable, which is the result of tossing two dice and looking at the sum of them. And the potential outcomes are 2 through 12, because you can get a minimum sum of 2 and a maximum of 12 by tossing each of these two dice. And this is the probability of getting each of the sums, depending on how many ways you can get it. Another common example of a discrete probability mass function is the uniform function. The uniform distribution of a finite sample space is one that assigns probability mass function 1 over n for n possible outcomes. We also have continuous random variables. So thus far we've been seeing discrete random variables that have a discrete set of possible outcomes. Continuous random variables can have any outcome defined within an interval in real valued space. And now the probability mass function would be replaced by a probability density function. And the probability density function, instead of summing over all potential outcomes, you would integrate over them because they all lie on a real line. And the probability of any event is the integral that represents that event. So here's an example. Each point in this probability density function only gives you the infinitesimal probability of any given value. So any event has to be an interval, and you have to integrate over it. For example, the event that you get between 0 and 1 standard deviation here is approximately 34.1%, or in probabilities 0.341. A continuous uniform distribution is the continuous analog of a discrete uniform distribution. If the total sample space is the interval A through B inclusive, then the uniform continuous distribution is basically a horizontal line at 1 over B minus A. Another kind of weird example is if you draw an arrow on a frisbee, throw it, and you see what angle the arrow is making with respect to magnetic north. You could make anything from 0 all the way to 2 pi. And this gives you a continuous set of values you can get. Another common example is our friend the Gaussian distribution, which you saw in a Gaussian kernel with slightly different parameters here. This can kind of describe phenomena that are clustered around the mean. For example, like the height of a person. So there's a lot of people that are of average height and relatively few people that are very tall or very short. When you have real data, usually the real data doesn't follow these very nice probability distribution functions, the canonical ones, such as the Gaussian or the uniform. So a lot of times you have to estimate a probability density function, implicitly or explicitly. Why? Because you might want to generate samples that are distributed like some data set. Or you might want to estimate something more interesting, such as how much information do two variables you measured on your observations have about each other. Or you might want to capture statistics about the entire stochasticity, such as variance or entropy, or reason about outliers or noise. So usually what you are given in real data is a set of samples from some underlying probability distribution that you don't have access to, and you have to estimate it. And one way of estimating it is as a discrete probability distribution by discretizing or binning the potential outcomes. This gives rise to what are called histograms. And histograms are examples of non-parametric estimates of density. That means that they don't follow a canonical distribution like a binomial or a Gaussian or something like that. Here, as an example, I'm using real mass cytometry data measuring two signaling molecules called phospho-CD3 and phospho-SLP76. Mostly in this lecture, I'll just be using the phospho-CD3 as a one-dimensional example. A really simple approach to understanding how this data is distributed in this x variable is to bin the data into equal width bins and just count up how many data points occurred in each bin. This gives you a histogram. This is a super simple way of doing it. It's an order of n algorithm if you have n data points. Let's say that you have about 10 bins, and then you just go over every data point and see which bin it falls into. But the width of the bin really matters. If you have 10 bins versus 5 bins, you're able to see this earlier peak at 0 that you're not able to see at the 5 bins. Also, if you use too many bins to get too accurate of an estimate, then you'll get non-smooth gaps, jumps, and discontinuities that aren't realistic. They're just sampling artifacts. So how can you fix this? You can try to actually estimate a continuous probability density function. And this is where kernel density estimates can come in. Kernel density estimates use the same kernels that we've been talking about before. For example, a uniform kernel that has constant value for a certain radius and then just drops to 0, or a Gaussian kernel. A kernel density estimate is found by taking these data points and putting a kernel over each data point, centered at each data point, and then integrating or summing up the kernel every place you want to estimate the kernel density at. This can actually give you something that's very different than the histogram. It can give you something that's really smooth and interpolates over gaps in the density. But this too has a dependence on width, or the bandwidth. For example, the bandwidth of the Gaussian kernel that you use. If you use very high bandwidths, you'll get an overly smooth estimate. You don't use a high enough bandwidth, you get a very jagged estimate. So what is the optimal bandwidth? There are heuristics for deciding that. One of them is called the Silverman's rule of thumb. And the Silverman's rule of thumb pretends the entire distribution is a Gaussian and solves for its optimal bandwidth using this formula here. And how does that work? It basically gives you something that would be an optimal bandwidth had your data been distributed as a Gaussian, which is usually pretty reasonable. Kernel density estimation, in a cinch, kind of looks like this with two-dimensional data. You have your data, you place a little kernel, here 2D Gaussian mini kernels at each point, then you integrate over this space, and it's rendered as a heat map. And here, when you've rendered this, you see that most of the density is here or here, and there's very little density everywhere else. And this gives you sort of a pseudo-continuous estimate of your density. Now, is this efficient? This is much less efficient, because if you want to estimate your kernel density at p points, then you have to look at the contribution of all of the n Gaussians centered at all the n data points at every one of your p points. Now, this might not be a huge problem in 1 dimensions, but what about 2 dimensions? In 2 dimensions, you want a grid of estimates, maybe 256 by 256, or 1024 by 1024. So this P actually grows exponentially with the dimensionality of your data. But still, for relatively low dimensions like 2 or 3, kernel density estimation is tractable. For higher dimensions, you can talk to me about graph-based estimations. So here we have it, the 3 concepts that we've talked about. Data and these random variables that you've observed in data, and then estimating the density using either bins, which results in a histogram, or kernels and integration, which results in a density estimate.